Hi everyone, this is Chen. Welcome back to my channel. This is another video on Olympiad geometry. This problem right here is problem number 3 from the APMO 2021. The APMO is the Asian Pacific Maths Olympiad. So as always, I encourage you to pause the video and try the problem out on your own. Please make the diagram and try to get as many ideas as you can. And then I'm going to show you a small and simple solution to this problem. And I'm going to give the hint in a bit, but first let me just show you my diagram here. So we have ABCD is a cyclic quadrilateral and gamma is its circumcircle. Then E is the intersection of the diagonals. So right here I've marked E. So BD intersection AC is the point E. L is the center of the circle tangent to the sides AB, BC, and CD. This was kind of like the tricky part. I mean, if you, when making the diagram on paper, this might not be obvious to some beginners, but essentially you can think of this as if I extend the side BA and I let it meet the side CD extended. So if let me try and make them to show you. So if I extend this side and call this point F maybe, then you could think of this triangle FBC. This triangle is going to have an in circle. So essentially this circle that they're talking about, the circle that's tangent to the sides AB, BC, and CD, that's essentially the in circle of the side FBC. And so the way to construct it would be just as any in circles. You would just make to find the center, you would just make the angle bisectors of side FBC and FCB, which is actually ABC. So the angle bisector of ABC and then DCB, let that meet at L. And then to make the circle, obviously you can just drop a perpendicular from L to any of these sides. Maybe call that point, I don't know, FG maybe, or E or H, anything. And then just make a circle centered at H with the radius of L and that whatever that point is. So that's how you would make this circle here. And then the question asked us to make the midpoint of the arc BC. So that's what the point here is. So MB is equal to MC. It's that point on the circle. And then they asked us to make the X-center. So the X-center is obviously you extend the side for EBC, you would extend the side EB, and essentially the external angle bisector of sides of EBC and ECB, they will meet here at this point G. I did not show these lines here, but that's what the point G is. It's the X-center. So hopefully now you know what all of these things are. And what the problem is we need to show that the points L, M, and G are collinear. And there's a number of ways to do this, but the way that I found like the most simple was in this case using Pascal's theorem. And I'll probably leave a link in the description for a video on it, but let me just give you a quick review on what Pascal's theorem is, and then maybe you can try and use the theorem here. So it's a beautiful theorem. Let me open up a new window here so you can see this is on GeoGebra. I wrote down the theorem. But this is just to show you how great the theorem is. I can actually, so here's what the theorem is. Suppose A, B, C, and then A prime, B prime, and C prime. So they're all 6 points. These 6 points are on a circle here. So now these are 6 points in any order. You can switch up the order as however you like. And now the really cool part is if you make the points, so the first point is the point AB prime intersection A prime B. Let me use this line tool here to make that point actually to show you. So A B prime and then B A prime. So it'll be somewhere here. Let me actually mark that point. So this is the point. GeoGebra is marking it as B again. Let me change the name to, I don't know, let's say D for now. then I'm going to make the other 2 points. So there's a point BC prime intersection with C prime B. So this is actually a way of writing the theorem which is kind of, I found really cool, because you don't really have to think a lot about which points and which intersections to make, and how do you get those collinear points. I encourage you to, obviously, before watching this, at this point, if you've not seen this theorem before, maybe watch the video in the description or look it up on AOPS or Brilliant. But for now, it's really simple actually. Just choose any 6 points and then label them this way. So A, B, C, A prime, B prime, C prime, and somehow magically, if you make these 3 intersection points of the 6 lines respectively, then the 3 points will be collinear. So let me show you the other points. So B, C prime. Let me just quickly make them. So B, C prime, B prime, C. That is another point right here. And then finally we have A, C prime. This is not that hard to learn, this notation. So A, it's kind of an easy order to memorize. So A, B prime, A prime, B. B, C prime, C prime, B. A, C prime, A prime, C. So I'm just going to go ahead and make that one. So, sorry, this is A prime. I made the wrong ones here. This should have been A, C prime, and A prime, C. And believe it or not, somehow magically, these 3 points, so this third point here is F. Believe it or not, D, E, and F are going to be collinear. And these 3 points will be collinear no matter what the circle is or how you switch up the order of the points. This is always going to be true. In fact, I'm going to show you. Let me move these points around. So if I take C and I bring it here, maybe, so, and then maybe let me take B, take this here, let me move things more. There can be many different representations of this theorem. Let me just make it a little, so it's not that messy anymore, maybe. So that's another one. This one. So you get the idea. So no matter how we make the circle, no matter how I'm moving the points, these 3 points always stay collinear. So essentially, these are the 3 intersection points of the 6 lines which are non-parallel. So as long as, obviously, if they're parallel, then they're never going to meet. So as long as that's true, these points are always going to meet. There's a configuration that I'm trying to show that's kind of neater, but yeah, this one looks like that. Okay, so as you can see here, this is kind of neater with these intersections are kind of, I guess, a little easier to see right here. So I want you to note this down if you haven't seen this before, and now try and use this to solve our problem. See how we can use Pascal's theorem there to show that these 3 points are collinear. So let me go back to the diagram right here, and let's try and think of how to use this. So we cannot use it on the circles, obviously the gamma circle or the smaller circle, because we need the 3 points, because none of the points can actually be on the circle. So right, M is on one of the circles, and then another point is like the center of the circle. So to do this, we're going to need a magical construction here. So it's not that hard to see why you would have to make that, because whenever you have like the midpoint of an arc, it can be a good idea to make this circle. So I'm going to make this circle with center M that passes through B and C. Now, why is this circle going to be important? Well, by the Incenter-Excenter lemma, if you don't know what that is, also look that up. So essentially, we know that this circle will have the incenter and the excenter of these two triangles. So triangle ABC, the incenter of this triangle will lie on this circle. But by the Incenter-Excenter lemma, it's a simple angle chase that shows that the incenter will be on this circle. So let me try and mark those two incenters and excenters. So where is the angle bisector? Let me quickly try and make them. I'm just going to make one angle bisector and mark the point where it meets the circle. So this, and actually let me rename it to IA. So this is going to be IA because it's the incenter of A. Let me move it around so you can see it. Oh, this one here and the L back up there. Okay. And similarly, I'm going to make the incenter of the triangle DBC. That's also going to be on this circle. Once again, by the same logic, the Incenter-Excenter lemma says that the midpoint of the arc is the center of the circle that passes through both the incenter and the excenter, and also the points B and C. So I'm going to now make the D incenter. So right there. And you might be noticing something right away. It's in the diagram, and we're now going to prove why that's true. So let me just first mark this point. It's actually not that hard to prove. I want you to prove something that you can see maybe right now that I'm constructing. You can see something that could be true, that actually, like, it looks to be very true, but you need to prove it. So try and prove it. Let me also make the excenter, so the external bisectors of the ABC and DBC. I'm going to have to make the lines properly then. It's going to take a second. Okay, so where's the angle bisector tool? It is somewhere. Okay. So there we go, number one. And this was right here. Oh wait, I think I made the wrong one. So I need to make this side and this side. Yeah, okay. I think I'm making the wrong one. Let me just do this one step again. So I extended AB right here, and I'm going to make the angle bisector of the external angle bisector. So this side and this side. What is going on? Okay, so this is a little weird. It should pass through G. Why is it not? Oh, let me actually extend the other ones too. Wait, I got it. So I should extend DB here. Sorry, this is getting a little messy. I'm just going to clear it up in a bit. And let's extend AC here. I'm going to hide the things that we don't need in a bit. So I'm going to make the external bisector here for DBC, right? So this side and this side, and this is the excenter. This is the D excenter right there. And then let me actually just make that one as well. So the A excenter will be right there at this point. So let me mark those two. So right away we can notice something. Let me mark these 2 points. Let me change their names. So this H is actually the AX center, and we know this because we know that A and the incenter of A and then the point M and the X center, they all have to be on a straight line. So actually, instead of making these bisectors, I should have just connected the lines. Never mind. But so I'm going to write this as EA, and this other one I'm going to call it ED. Sorry for the extra time in making the diagram. Now let me just hide all of the unnecessary stuff. So just 1 second. Are we good? Yeah, I think we are. One more line. So I think we're done with drawing all that we needed to. So now we can just finish up writing the proof. So after constructing these lines, so these points, the X centers and the incenters, we figured something out. We saw that the points, there were some things that were collinear. And essentially, we know that B, the incenter, the A incenter of ABC, the incenter of ABC, and L, they're all on a straight line. And obviously, even if you drew it on paper, you would see that they are collinear from your diagram. And then it's just about trying to prove this, because notice if we can prove this, then we are done. But by Pascal's theorem, because these are essentially, we know that these are the 3 points which are the intersections of 6 lines here. If this is true, if B, I, A, and L are collinear and C, I, D, and L are collinear, so then L is the intersection of, so we have 6 points on a circle here. We have C, we have ID, IA, B, ED, and EA. So all of them are on a circle. And if this is true, that these are collinear, then we are essentially done by Pascal's theorem, because we know by the Incenter-Excenter method already that I, A, M, and EA are on a straight line. That's pretty obvious. And ID, M, and ED are on a straight line. So then this is very similar to this construction that we had here. Right here, this is just like delta little, but essentially we have 6 points, and then we have the intersections of 6 of them respectively, which are non-parallel here. So we have the intersection CID, intersection BIA, which is L, and then we have IA, intersection EA, IA. We have the intersection of IA, EA with ED, ID, and BED with the other one, which is let me just copy this right here and put it into the blackboard so I can just start writing up the proof. So let me just paste it right on top of this. So now let me just quickly write the proof. There's only one thing that's left that we need to do. We need to show that these things, these lines, these points, the points that we said that B, I, A, and L are collinear, and C, I, D, and L are collinear, and similarly B, E, D, and G, and C, E, A, and G. If we can show they're collinear, then we are done. And that's actually pretty obvious. So let's first start writing the proof. So let's call this new circle omega. So let omega be circle centered at M and passing through B and C. Now by the Incenter-Excenter lemma, we know that Excenter lemma we know that essentially the incenters and excenters of both triangle ABC and triangle DBC. They all lie on this circle, this omega. And then there's just one thing we need to notice, because remember how we constructed L. So L was the intersection of the angle bisectors of angle ABC and angle DCB. So, but by definition we know that IA is also on the angle bisector of ABC, because it's the essentially it's the incenter. So we can say that IA and L are both on the bisector of angle ABC. Similarly, we can say that for the external bisector, or actually let's just for the external bisector. So this is the internal one. For the external one, we know that EA and G, where G is the X circle of EBC, they are both on the bisector of, once again, ACB. Right? So yeah, ACB. And so that's why we know that B, IA, and L collinear. I'm kind of running out of space here. And also C, EA, and G are collinear. Let me scroll down so I have some more space to finish this up. Okay. Let me also change the color and try to write a little better in terms of handwriting. Okay, so once again, using the same logic, I can write down that C, ID, and L collinear, and B, ED, and G collinear. Once again, why? Because ID and L are both on the internal angle bisector of angle DCB, and similarly for the external angle bisector of angle DBC, we know that ED and G both lie on them, just because of the way they're defined. And so then by Pascal's theorem, on the circle, which is CID and then IA, B, ED, and EA, the intersections of, well, BIA intersection with CID, which is equal to L, that's 1 point, and then IA, EA, that's a line segment, the intersection of that with ED, ID, that's equal to M, and then the third point is the intersection of BED with CEA, that is equal to G. So by Pascal's theorem, all of these points, we know that they are collinear. So L, M, and G are collinear, and we are done. Just by Pascal's theorem, we are done. And I leave it as an exercise to figure out what are the A, B, C, and A prime, B prime, and C prime in this case for you. So like, what would the order be? It doesn't really matter, but essentially this completes the proof that just by seeing a bunch of stuff, by making a construction and then noting some claims and then using them and finishing up by Pascal's theorem, we are done.